Okay, the other situation we looked at was where we have a sphere rolling down an incline and a hoop rolling down an incline. Now this is presented very nicely, good diagrams, and the hypothesis that the distances are the same, the masses are the same, and I believe the problem stated that the angles are the same. That wasn't mentioned, but we'll regard that as implicit. And then I better double check and see whether I really said it. Okay. So with all those things being equal, the question then is, do we have the same, do these things attain the same velocity at the end of that displacement? Okay, so we got a very good picture here. Picture of our mass, normal force, our gravitational force vector. Now we had a V10 here, and actually I would have said a delta S vector here. So I'm going to kind of impose delta S here, because what happened was the individual presenting this started thinking in terms of velocities and accelerations, which is a terrible idea, as we'll see. It just makes things way more complicated than the energy picture. So I'm going to go to a delta S so that we can see from this picture that your projection of FV onto delta S rather than onto V1, so I'm going to make that little change with all due respect, is your gravitational force parallel. Then, and I intervened and wrote this down because, again, calculating your acceleration, well, in the first place, this is not your acceleration. If you divide this force by your mass, even assuming no friction, and that is the implicit assumption, I think it might have been explicit, no friction loss, you still don't have this. And the reasons for that are easiest to understand in terms of the energy picture. If you try to understand it in terms of the force picture, it's a little more complicated. So we're going to kind of throw that out. We don't want to think about it that way. And we don't want to think about this, although if you knew what the acceleration was, this would be a valid equation. It just says that V1 of t equals V1 dot plus your acceleration parallel times t. Okay? It's not an invalid equation, but you're not going to get that acceleration very easily. Now you can figure it out after you figure out the energy, and we'll see. Okay, so what I did write down, and then we proceeded from there. The change in potential energy for the first mass is m1g times delta S, dot delta S, g, m1g, your force vector, dot your delta S vector, using the dot product definition of work. And same thing for your second mass, but since the masses are the same and delta S is the same in both cases, we find that the change in potential energy is the same on both ramps. Now, where do you go from there? Because I kind of wrote this down and then turned you loose. And, well, okay, then the presenter said, okay, well, okay, then in that case, if there are no dissipative forces, the work energy theorem tells us that the kinetic energy changes have to be the same. And then started to write down that 1/2 m1 v1 delta v1 squared equals 1/2 m2 times delta v2 squared, or something like that. And now, you can't do that. You got to get all the kinetic energy. And actually, I think the person included the I omega squared. Now, there's an error in the way this is written. Okay, this should be, now with the hypothesis or the premise that these things both start from rest, it's not actually incorrect, but it's very bad form. This would be 1/2 m1 times the change in v squared. Not the square of the change in v, but the change in v squared, because of course that would be then 1/2 m1 vf squared minus 1/2 m1 v naught squared. Very important distinction. Don't fall into that trap and make that mistake. Then you subtract your 1/2 I, and we wrote down delta omega squared, but it's delta of omega squared, not the square of delta omega. Make sure you understand thoroughly why that is. Now, it didn't use parentheses here, so that's a good thing. I can just insert the parentheses and make these correct. Then we get to the essence of the situation. Okay, this is actually written correctly. We don't know the moment of inertia for the sphere, although we should know the formula at least by the time we take the exam. And hopefully how to do the integration is a calculus 1 integral to get the expression for that moment of inertia. But digressing from that, we don't know the moment of inertia of the first object, the solid sphere, but the second object is a hoop with all the mass out there at the rim, so its moment of inertia is its mass times its radius squared. So this is actually valid, but really the simplest way to see this is that, and I don't have a good place to write this, so I'm going to pose on this little space here. Okay, your kinetic energies, 1/2 m1 times the change in v1 squared plus 1/2 I1 times the change in omega 1 squared equals 1/2 m2 delta of v2 squared, and really my parentheses should go there, and I'm not going to worry about that one, plus 1/2, I hope you can read this, I2 times a change in omega 2 squared. The key is that the moment of inertia is the sum of all the mr squared quantities for every particle in the sphere or the hoop. And the r squareds for the hoop, well, since all the mass is at the rim of the hoop, all the r squareds for the hoop are equal to the total radius of the hoop. Whereas the r squareds in this thing are mostly inside the radius. There's only a small film of particles that are essentially at distance r, and all the rest of them are at a distance equal to the radius, and all the rest are closer to the center. So that we conclude that I2 is greater than I1. Now, what does that tell us? Well, M2 is equal to M1, I2 is greater than I1, so we can conclude that you have more kinetic energy at the same speed in this than in this. Now, there's much more to be done, but with that conclusion, we see that since you're taking more of the potential energy loss and putting it into relative, you're taking a greater relative share of the potential energy loss and putting it into the rotational kinetic energy of the hoop than you are for the sphere. Meaning that the hoop is going to go down more slowly. The sphere is going to beat the hoop. Because of course that leaves more kinetic energy over here in the translation of the velocity, the V-type kinetic energy. Now, that's all I'm going to say about it, but everybody needs to try to move further into this problem.